Howdy, welcome to the Smart Grid Center webinar titled Asset Management in Distribution Systems with Distributed Renewable Generation. I'm Andrea Kishney from the Smart Grid Center. First, let me ask you to send a question in the Zoom chat window anytime to get it answered at the end of the presentation, or raise your hand with the hand button, and I will allow you to unmute yourself and ask questions or share your comments after the talk. The presenters today are Dr. Miroslav Begovic, department head and Moore professor, and his PhD student Aki Pirzada, a teaching fellow at the Electrical and Computer Engineering department at Texas A&M University. Dr. Begovic, prior to joining A&M, was professor and chair of the Electric Energy Research Group in the School of Electrical and Computer Engineering and affiliated faculty member at the Breyers Institute for Sustainable Systems and University Center of Excellence in Photovoltaic Research at Georgia Tech. He has been a member of the IEEE Power System Relaying Committee for 2 decades, chaired a number of its working groups, and served as president of the IEEE Power and Energy Society. He was an IEEE fellow and recipient of the IEEE 2019 Meritorious Service Award. Mr. Pirzada, prior to his PhD studies, received his master's degree in electrical engineering from Texas A&M in 2018, and his bachelor degree in electrical engineering from the National Institute of Technology in India in 2011. He also served as an operational and design engineer at NTPC Ltd, one of the largest generation utilities in the world, for over 3 years. Now I'm turning it over to Mr. Dr. Begovic and Mr. Pirzada.
Thank you, Andrea. I appreciate the kind introduction, and we will try to proceed with presentation because we have many slides and interesting topic which we hope will be of interest to our audience today. So the issue of asset management, and especially in distribution systems, is quite important. Utilities nowadays have billions of dollars of, how do I switch? We're trying to, okay. Utilities have billions of dollars in aging systems that have multiple units, transformers, breakers, protection systems, underground cables, overhead lines, wood poles in many cases, which are aging, and because of the size and extensive nature of power systems, many of those devices are well beyond their original design life, which doesn't mean anything because they can function sometimes twice as long, but sometimes fail before they reach their designed life. So the demand for system output and availability is higher now than it has ever been in the past. People take for granted presence of electricity wherever they go. And we have to provide them with that kind of reliability and that kind of resilience to increasingly frequent events that are threatening the system performance. So maintenance budgets to replace and maintain those devices, all kinds of them, are not as large because those are multi-billion-dollar infrastructures. And we will try to, we're trying to figure out how do we, so do I just click on this? Yeah, okay, or this. Asset management is a general area that enables us to facilitate this process of looking into a large infrastructure, identifying units that are at risk. And that means scheduling of maintenance, periodic maintenance, prolongs the life because it may prevent some of the failures, follow up on those, setting objectives on what should be part of the planning on replacements and budgeting for adequate investment into it, collecting data and performance of the system and analyzing all those factors are part of the asset management. So optimization problem that comes out of it is based on achieving goals based on the best information that's available, and many utilities are not known for collecting all the necessary information to make an informed decision. There are two possible approaches. One is having a finite known amount of resources, meaning dollars, determine the most effective means of spreading them so that the reliability and performance of the system are superior to any other solution. Or given a desired level of reliability, determine what kind of resources are needed for it. So utilities employ these asset management strategies for all kinds of things, and we will outline some of them. Corrective strategies are, we wait for a unit to fail, say a transformer, then we repair or replace it. Another possibility is for cables, for example, we may try to identify those that are at risk and then replace portions of the underground cables in distribution networks prior to failing, thus eliminating or shortening the amount of time spent on their repair, during which time customers don't receive enough, don't receive a supply. Third possibility is to monitor the condition of assets, say transformers again, or even cables, and try to identify when they become prone to failing. And the fourth one is to center it all around reliability and use monitoring control information and systems external condition, exposure to strong fields and weather conditions, and calculate what reliability factors should be satisfied. Utilities are not known for collecting extensive historical data, so in many cases these decisions are made on very partial, imperfect data, and we will try to present one quick example of how it's done on utility distribution network cable systems, and then Akib will talk about another problem that arises in distribution networks that have significant presence of photovoltaic generators. So we have an aging system, let's say a distribution network with a lot of underground cables bringing from the main substation power to all the households or commercial facilities. That system is aging, so we design for it a maintenance plan, and then we try to predict the failures, and we try to use some diagnostics that enables us to do so effectively. Then we have to face the reality and operate with economic constraints of finite resources and incorporate all of that into a maintenance plan. So statistical approaches and heuristic approaches are the ones that are commonly used to use the necessary monitoring information and transform it into actionable things such as replacement, preventive replacement or repair, periodic maintenance, period setting, and so forth. So I won't go into details of these different approaches, but rather try to show how this simulation works. We have data inputs which show us installations, replacements and repairs or failures of the system. We have a stochastic prediction algorithms that takes advantage of those data and creates predictions of vulnerabilities. Those additional inputs that we might need is the confidence level with which we would like to obtain that information, because it's stochastic, it's not accurate, it is representing a system that can fail at any moment, but because a lot of them are installed, they tend to fail within certain distribution of times, and we are trying to get more information by experiencing those breakdowns and incorporating them in our calculations. The output of that are action levels and failure predictions. So this model derivation in practice means that starting with a hazard function, which transformed in words is the probability of an imminent failure, assuming that the failure hasn't been experienced up to the time t, that hazard function show us whether or not the unit should be replaced or not. If the hazard is increasing, that means the probability of a failure is increasing, and it can be calculated for multi-year installations and at a certain period of time by looking into cumulative hazard function for multiple devices. Similarly, if devices are behaving such that hazard function is represented by Weibull distribution, which is very commonly used for devices like this in normal operation with long lifetimes, but which eventually fail, we can calculate these hazards and estimate the problems. What's happening with cables? This graph, this picture shows just many mechanisms that are usually happening in the insulations of cables. This is a half of the cross section of a typical underground cable. I won't go into details of all of those. That could take probably a good chunk of a few days to talk about all things that happen in the cables, but we're trying to simplify that to the point of understanding how those different technologies of cables are being addressed and replaced in normal operating regime. These are 4 technologies used in cables: extruded polyethylene, cross-linked polyethylene, and various modifications. So from early 1960s to the turn of the century, you see how the amount of cables installed has been increasing, and how all those different technologies, which differently age and differently act, have been installed. So what we are trying to associate with all of them is a moment of installation, and then a time during which the number of failures in such a system are growing. So let's say we install at year 100 miles of cable. In different segments of that cable, we will be experiencing failures over time, and they will be growing up to a point of partial replacement, when hopefully the new cable that is being replaced, that is replacing an old one, causes reduction in failures. And with that information, we try to address the issue of cable system, which has many installation years and many partial replacement events, which are replacing aging portions of the cable. Then we try to calculate for that compound system the distribution, upper and lower bound, of the number of failures that are being expected. And usually that number is the driver from which to calculate future replacement events. So the net effect should be the net failure reduction compared to the growth of failures that would be happening without any actions. This is typically what the data that utilities provide look like. In year number 1, you have so many miles installed, so many miles replaced, and number of failures, and then you combine all of that for many years of operation and use that to calculate these curves, the failure curves, with n installs, then the prediction for year number 1 with new installs. When you add those 2 functions, you get the total overall number of failures. And since that is distribution, we are actually calculating it using these Weibull distribution formulations. And what we get is the certain interval of or confidence range of failures that we can tolerate in the system, and calculate how much replacement should be secured to achieve that. Then the outcome are distributions of failures that are obtained on the basis of that information. And when replacements happen, we will be experiencing a downward trend, and that can be seen here. So the confidence range without replacements points to the distribution of outcomes of the failures in the propagating into the year X+1 once the present measurements of year X and all the previous years have been incorporated. And when we do the replacement, we estimate that that curve will be shifted downwards by the amount that would hopefully justify the expenditures of those partial replacements. And then looking into the spread of these, which can be obtained by using the Weibull distribution, we can calculate the final curve, which is the replacements in miles of distribution cables versus confidence that those replacements in terms of their coverage of the entire distribution function will be doing. So if we want a 90% confidence that we will be experiencing the desired but not higher number of failures, we will need to replace certain amount of miles. On this graph, it's a little less than 400 miles. But if we want to increase that confidence by 5%, and these are actual numbers obtained from system that utilities in the Midwest have provided us with, we see that we have to up the installations by about 20 miles in order to increase the confidence range by 5%. So the takeaways of this process, which I understand is very quickly described and perhaps not conducive to thorough understanding of it, is that we deal with historical records of equipment failures, which are not including information about breakdowns, about exposures to extreme fields, moisture and extreme weather, and then using statistical failure model, using on the available data, performing then Monte Carlo simulations with that model, identifying the characteristics of the viable functions, and then based on that, estimated the effect of replacement rates, assuming that new replaced devices will be acting for a while with very few failures and only beginning to develop failures after prolonged exposure. So this is tracking of the failure performance and monitoring failure information as those replacements are going forward, increases the knowledge of the system and enables utilities to prevent failures from actually occurring and long outages to be the drivers to replacements, keeping customers happier and utilities spending less money and earning more money by avoiding those prolonged outage events. So I will, at this point, stop talking about this and let Akib address a more important and more interesting subject, which is how do we deal with distribution and aging of the equipment that is caused by presence of the photovoltaic systems across distribution network. Akib?
Howdy all. I am Akib Rizada, and I'll try to walk you through a slightly different version of the asset management problem, one that is concerned with the lifetimes of switched mechanical devices such as voltage regulators and capacitor banks. We have those devices on our distribution feeders to provide voltage control and also do reactive power compensation. So here's an example of, this is a one-line diagram of a typical distribution network. We have a source bus that's connected to the sub-transmission or transmission networks. And all the black circles on this one-line diagram represent load points. So these are the points where we have loads connected to the feeder. And this symbol is represents a voltage regulator. And here is an actual picture of what a regulator looks like. And we also have capacitor banks at the far end of the feeder. And here is another picture of what a three-phase bank looks like. So voltage regulators are placed there to control the voltage along the length of the feeder. And we have capacitor banks to minimize losses since they are there for correcting the power factor. So here is the same distribution feeder. The difference is that in this case, we have removed the voltage regulators and capacitor banks. And if you take this feeder and do a power flow simulation on this feeder, assuming that the loads are the peak values, and we try to determine the voltages at each of the load buses. And here is the voltage plot. As we go away from the source bus, that is from the substation, we see that there's a progressive decline in the voltages. And the buses that are shown in the shaded region are the voltages are of these buses. And we can see that pretty soon we are having voltages that go outside acceptable limits. But when we connect these devices back at their optimal locations, we have an improved voltage profile. So for example, if you take a look at the first regulator that's connected between bus 814 and 850, we'll see that the voltage at bus 850 has increased. And as we move further along the length of this feeder, the voltages begin to drop until we hit the second regulator, which is connected between buses 842 and 832. And we see that the voltage is again increasing at the bus 832. So what happens when we have distributed generation in the form of distributed rooftop photovoltaic generators. So here is the same feeder. The difference is that now we have connected some PV generators at the far end of the feeder, and we redo the power flow to determine the voltages at each of these buses. And we find that the buses where we have connected these PV generators, the voltage has increased. And in fact, in 2 of those buses, we have voltages that are outside acceptable limits. So sure, we can always control the settings of these regulators to make sure that our voltage always stays within this bandwidth. But if you have enough distributed generation on this feeder, at some point, the regulators will not be able to correct for that voltage, as is happening in this case. So here is the operating principle of a voltage regulator. We have 3 important parameters. We have a voltage set point, the bandwidth, and the time delay. So for example, if you'll take a look at this graph here on the top, this is a plot of voltage plotted as a function of time. So as long as we can see, as long as the voltage stays within the bandwidth, our regulator does not register any operations. But as soon as our voltage goes outside the limit, in this case, the voltage is dropping and then falling below the lower limit. So what happens is that the transformer increases its taps. So it changes its tap position to bring this voltage back into this bandwidth. And the opposite happens when we have voltages exceeding the upper limit. In that case, the transformer tries to decrease its tap position so as to bring the voltage back into the acceptable limit. And as long as the voltage stays within this bandwidth, the transformer or the tap changer does not register any operations. So in this graph here, each step change represents one operation of a tap changer. So now let's try to look at this problem more intuitively. So we have, take a look at the picture on the left-hand side. We have a very bright sunny day. And if we have a solar panel that's connected to our network, and if you take a look at the irradiance or the amount of sunlight that's falling on the panel, we'll see that the irradiance follows a very smooth curve since we're having a bright sunny day with no clouds. But imagine a scenario where a cloud just swoops in and blocks the sunlight that's falling on the solar panel. So at that point, there will be a dip in the irradiance profile and hence a dip in the generation as well. But we might have a situation, and it's important to remember that these solar PV curves, they keep on changing throughout the year, depending upon the sun's position in the sky. We might have a situation where we have intermittent clouds. So we have lots of these clouds randomly moving and blocking the sunlight that's hitting the panel. So in that case, we will have an irradiance profile that has these rapid changes. And if we were to calculate the power that's injected into the network that's coming in from this PV system, the generation will also experience similar rapid changes. Now, the voltage at this point where our PV is connected to the network, the voltage profile looks something like this with rapidly changing voltage. Now, such a voltage profile can wreak havoc on our regulators and capacitor banks since they are mechanical devices, and these changes happen in the time scales of minutes or even seconds. So when you have enough distributed generation, and that means there is an increased likelihood of your voltages being highly variable, that will stretch these devices to the limits of their operation and hence cause accelerated wear and tear of these devices, and they might fail much early than they were designed for. So let's see what a variable voltage does to the operation of these devices. On the left side, we have a voltage plot as a function of time, and we have 2 curves, the blue and the red curve. The blue curve is the voltage without any distributed generation. The red curve is the voltage at the same location with distributed generation. So 2 things happen. As soon as the DG turns on, the voltages at that point increase, and not only do they increase, but there's an increased variability as well. And this happens until DG is generating power, and when it turns off, the 2 curves meet. And if you take a look at what is happening with our total load tap changers, again, we have 2 curves. The blue curve corresponds to the blue voltage profile. The red curve corresponds to the red voltage profile. And you can see each step change here represents one operation. So when we have a highly variable voltage, you can see how it forces the regulator to operate outside its design limits. And in this particular case, we have our tap changer is registering 13 times more operations than normal, than what it was designed for. So let's take a quick look at some of the statistics of the failure transformers. These are the results of two surveys done in early 2000, and which show that the failure in OLTCs dominate the failures of distribution transformers. And here are the results of a more recent survey. This was done in Australia in 2018. And if you take a look at the picture on the top left, we see that amongst the three categories of transformers analyzed, the distribution, subtransmission, and the transmission, for distribution transformers, aging-related failures dominate. So the researchers here have used Weibull distributions to fit the data, and they have come up with a value of, so beta is a shape parameter of the Weibull distribution, and they have come up with a value of 3.5. So any value that's greater than 1 refers to an aging-related failure. So if you take a look at this picture on the top left, this is the hazard function plotted with age. And if we focus our attention on this blue curve, which is the hazard curves for distribution transformers, we'll see that after about 20 years of age, the hazard function experiences an exponential increase, which means that the probability of an immediate failure after 20 years increases. And if we take a look at this picture on top, on the bottom here, this is for distribution transformers, and we'll see that after about 20 years of age, the failures in OLTC dominate the failures happening in distribution transformers. So for what we conclude here is that for distribution transformers, aging failures dominate, and among aging failures, it is the OLTC and winding as well that dominate the aging-related failures. So here is a look at how solar PV consumption has grown over the past and what the future projections are. In the US, the consumption has grown from about 0.52 terawatt hours in 2000 to roughly about 56 terawatt hours. This is in 2016. And last year, the projected installed capacity was roughly around 69 megawatts, which was enough to power 13 million American homes. And as far as Texas is concerned, these are the Texas solar installations for each year over the past 10 years. And we can see that how the annual installations are growing in Texas. And right now we have enough solar to power over 1 million homes. And as far as the next 5 years are concerned, Texas is projected to add more than 23,000 megawatts of solar over the next 5 years. So when you consider the entire grid of Texas, and when you consider a substantial amount of distributed generation, you can see how these failures might begin to cascade across the Texas grid. And here is so here's an example of one such grid. This is a synthetic transmission and distribution grid. This is built on the footprint of Austin metropolitan area. So if we just focus on the distribution system, we have about 6 areas with a total of 128 substations and roughly about 450 feeders. So assuming 1 regulator per feeder, we have at least 450 feeders in this system. And it's possible that many feeders have more than 1 regulators, especially feeders of long radial length, which require more regulators to control the voltage. So and when we extrapolate this to cover the entire state of Texas, we are potentially looking at tens and thousands of these mechanical devices that are prone to failure as we keep on adding more distributed generation. So the asset management problem is we are trying to determine a failure model that can help us estimate the remaining life. That's the primary objective. And the model should have some features. First, it should be able to capture the impact of distributed generation. The hazard function of the model should be consistent with aging. Also, since utilities, they don't really have complete failure data sets, what they usually have is what we call the sensor data, which is incomplete data sets. So the model should be compatible with these types of data sets. And also the model should be able to incorporate expert knowledge. So utilities have been operating these devices for decades now, and they have accumulated a lot of knowledge about the failure of these devices. So what we do to address these conditions is we propose the use of inverse power law combined with a Weibull density model, and to make sure that our model is compatible with the data that's available and also can incorporate expert knowledge, we propose an inference scheme that works with sensor data. So when we combine the two, we end up with a failure prediction, a model that learns based on the past historical data and can make predictions about failures that might happen in the group of transformers that is still surviving. So to model the impact of distributed generation, what we do is we run annualized experiments on distribution test feeders, and we calculate the number of times these regulators operate in 1 year. So for example, if you take a look at this picture on the top right, the blue curve represents the annual operations of these tap regulators when we don't consider any distributed generation. But when we do consider some, in this case, 30% of DG, you'll see that at the end of the year, our regulators operate much more frequently. They register more operations as compared to the case when we don't have any DG. So as we keep on increasing the amount of distributed generation, so for example, in this case, we have 60%, and percent here refers to the percentage of the peak load. So if the peak load is, let's say, 1,000 megawatts, a 30% distributed generation would mean 300 megawatts of distributed generation. So you can see as we keep on increasing the capacity of the distributed generation, this gap between the number of operations widens. And at 90%, you'll see that this gap increases furthermore. So one possible indirect measure of the stress that's imposed on these regulators is the ratio of the number of operations with DG and without DG. And we use this ratio as sort of like an indirect measure of the stress that's imposed on these regulators. So the inverse power law has been successfully used to determine the lifetimes of power equipment when exposed to a certain stress. So this works with mechanical stresses, thermal stresses, or even electrical stresses. But in this case, we are only concerned with mechanical stresses. So the lifetime as a function of mechanical stress M is given as L0 and the ratio of the stress imposed, and N is the stress coefficient. And in this, here we take a look at what happens to the lifetime as a function of this stress. So we can have a quadratic increase in stress, a linear increase in stress, or a cubic increase in stress, and you'll see that it severely limits the lifetime of any power equipment. And we also consider a variable density function. Here we have a 2-parameter variable density function. Beta is the shape parameter and eta is the scale parameter. And on the bottom, we have different variable plots for different values of these variables. So for a constant shape parameter, if we reduce the scale parameter, our variable density function keeps shifting to the left. And also the probability also increases. So you can see that you can compare the purple curve with the blue curve. Not only has the purple curve shifted to the left, but the probability has also gone up. So what we do in our failure model is we combine the two by replacing the scale parameter of a variable distribution with the inverse power law. And we end up with a density function that looks like this. And we call this the IPL variable failure density model. This is characterized by 3 parameters. We have a shape, scale, and a stress parameter. And the next challenge lies in estimating these parameters given some historical data. So as is true with all models, we first use some change of variables to reparameterize the model to make it more tractable. And we end up with a reparameterized failure model. And we can always go back to the original modeling by doing the inverse transformation. So before we can actually use some statistical inference scheme to estimate the parameters, we want to make sure that the data that we have actually comes from the model that we're proposing. And to do that, we do the Kolmogorov-Smirnov test on our data. So here in this table, you'll see some survivor data of a number of transformers. So we start with 40 transformers, and in 10 years, we have failures in 20 of them, and the 20 are still surviving. So we do the empirical CDF of this data, and we also plug this data into a model and get the viable, the CDF that's predicted by the model. So in this case, the case test result is true, which means the hypothesis, our hypothesis that this data comes from the model that we are proposing is true. So once this is true, we can go ahead and start estimating the parameters of the model. And to do that, we use the Bayesian inference scheme. A key idea in Bayesian inference is that the parameter of interest is a random variable. So one quick example to understand how Bayesian inference works is, suppose we are asked to find the bias of a coin. What Bayesian inference does, this is based on Bayes' rules. So it tells us that the probability of observing, let theta be the probability of getting heads. So the probability of getting heads when we do a coin toss, It's the product of our prior belief in that probability and the likelihood function. So x1 is the result of our experiment. It could be either heads or tails, and theta is the variable here. So when we do another coin toss, so now the probability of getting heads with 2 coin tosses is our likelihood function times our prior belief. But in this case, or we update our prior beliefs. So we, in the first case, the probability we got, this is the posterior, we replace our prior belief with this posterior. And as we keep on doing these coin tosses, let's suppose we do xn of these coin tosses. At the end of it, we will have the probability of getting theta given n number of xn number of coin tosses. It's just the prior belief that we started with and this product term. So looking at it graphically, what it means, suppose we have a coin which has a bias of 75%, which means that if we do enough coin tosses, we are, the likelihood of the probability of getting heads is 75%. So when we do the first toss, our prior and posterior are very close to each other. But as we keep on doing more coin tosses, the posterior not only begins to shift to the true value, but the uncertainty or the variance associated with this distribution also begins to decrease. And after 1,000 tosses, in this case, our posterior is fully concentrated around the true value, and our prior is prior is here. So you can see that as we acquire more data, we are getting closer to the true value. And we use the same idea to calculate the parameters of our model. Here is the central statement of the Bayesian inference. It tells us that the posterior of any unknown parameter conditioned on some data is the product of our prior belief in that parameter and the likelihood function. And the term in the denominator is just to normalize these probabilities. But the key difference is that now we are working with censored data instead of complete data. So censored data means, let's say we start with n devices at t equal to 0, and after some time, one of the devices will fail, and we will have progressive failures as time moves on. So let's say up until the present time moment, out of the n devices, R have failed, and so we have n minus R survivors. So what the problem is, here we want to make an inference on the survivors based on the transformers that have failed. So mathematically, we can write our data set has this form, and we plug this data set into this equation to get the posterior of the parameters. So here is the learning algorithm. We start with some prior belief. We combine the prior belief with our data that we have, and we arrive at the likelihood function. And once we have the likelihood function of the model, we can do a couple of things. We can get the posterior distributions. We can get the expected values of these parameters. And when we have all of that, we can plug those values back into the model to get a better estimate of the population that is still in operation. This estimate is better, but because it incorporates the information that's present to us in this data set. And here's how we go from data to an actual estimate. So if we focus on the flowchart here, we start with some failure data. So we have a random sample of failures and a random sample of survivors. From this failure data, we plug these values into our failure model, and we combine this with the prior belief. So we multiply these two to get what we call the joint conditional posterior parameters. So from there, we can obtain the marginal posterior parameters by integrating out the parameters that we don't want. And once we have the marginal conditional posteriors, this is just a probability distribution, we can get the expected values of these random variables. And when we do this for all the variables, we plug them back into the model to get a failure estimate. And then the process repeats. We acquire more data and repeat the whole process until we completely use up our failure database. So this is how we use the historical data to make a prediction about failures that have not been observed up until now. So let's look at an illustrative example. This is based on the IEEE 34 bus test feeder. So we consider 3 use cases. We have a baseline case where we don't consider any DG. We have a low PV penetration case and a high PV penetration case. And when we run the failure analysis on these 3 scenarios, these are results. So if we look at the top plot, these are the density functions for 3 different scenarios. So the blue curve is the failure density when we don't consider any distributed generation. The red curve is the failure density for 30%, and the black curve is the failure density for 90%. So you can see as we keep on adding more DG, our failure density curves, they keep shifting to the left, which means shorter lifespans, and the probability of observing a failure also goes up. And if you take a look at hazard rates with higher DG in our system, the probability of an immediate failure also increases. And also, if you take a look at survival plots, here we have the survival probability. With 90% PV, for example, the survival probability beyond 10 years drops to roughly about 10% from 50% in the no PV scenario. So there is a significant reduction in the lifetime of these devices, considering high penetrations of distributed generation. And this is how acquiring more information affects our estimates. So if you start with R equal to 1, which is if we know the failure time of just one device, then our model prediction is given by this blue curve, which is not accurate. But as we keep on acquiring more information, the model estimate improves. And with half the failure information available to us, we are in a position to make better estimates about the in-service population. Now, how do you manage these lifetimes of mechanical devices? Well, one possible solution is to look at solid-state-based devices. And here's a picture of an experimental setup. This is a capacitorless DStatCom developed here at XZM by the research team of Professor Robert Begovic. These devices, devices like this can either supersede the mechanical devices, or they can work together with the mechanical devices to maintain optimal system operation. And this is a multifunctional device, which means that it can perform multiple functions. For example, this particular device can do voltage control, it can do harmonic filtering, it can also provide reactive power compensation all at the same time. So when we consider a DStatCom in our network and we redo the failure analysis, on the left, on this picture on the left, we have the density functions plotted with and without the DStatCom. You can see the blue curve is without the DStatCom and the red curve is with the DStatCom. So with having this device, and we are considering 90% penetration of DG. So with DStatCom, not only are we extending the lifespans of these devices, but the probability of failure also drops. And if we look at the survival plots, we can see again with DStatCom, there is a much more likelihood that a device will survive beyond any T years of age. Now, if taking a look at the costs, since budget is at the heart of asset management problem, this data comes from the real world. So for example, an LTC transformer, if we are considering a 30-year lifespan, it will cost about roughly around $300,000, including maintenance, assuming that maintenance happens every 5 years. And for a single phase regulator, the cost is roughly about $150,000. So when we consider these costs in our model, so we really have two scenarios. We have a cost of doing nothing. So we keep on increasing our penetration of distributed generation, but that will mean we will have more device failures and hence more replacement costs. It also means that we'll have to do more maintenance of these devices. Or there's a cost of solution. So considering a solid state-based solution, the cost is the initial investment in the device, and with little to no maintenance required. And then the benefits are we get savings in terms of device failures, and there's also decreased maintenance of these devices. And here is a cost distribution curve for these two scenarios. For the blue curve is the cost distribution when we do nothing. So we keep on increasing distributed generation, and considering a 30-year lifespan, the expected value of the cost is closer to $650,000 over 30 years. But when we have DStatCom on our network and we redo the failure analysis, the expected value of the cost curve is roughly closer to $400,000. So that's a saving of $200,000 over a lifespan of 30 years. Assuming that we don't change our maintenance strategies and assuming that there's no maintenance cost involved in DStatCom. So in conclusion, we have an aging model of these mechanical assets that incorporates not only the stress, but also the expert knowledge. This model is compatible with censored failure data that's available, that's usually available with the utilities. And we conclude that having a high capacity of distributed generation severely affects the lifetime of these devices. In our particular example, the survival probability drops to less than 10% beyond 10 years. as opposed to more than 50% in the absence of any distributed generation. And our model, since it's able to incorporate prior belief, and with each, and as we keep acquiring more failure data, the model also shows convergence, remarkable convergence to the true value. And with that, I end this presentation and I open the floor for questions.
Akif, there are questions in the Q&A window and also in the chat window. If you could please, with Dr. Begovic, if you could address those questions, please.
Yes, so I'll address the first question about the number of mechanical operations. Yes, thermal loading. So in here, we are only considering mechanical stresses imposed on the tap changers. But there is, so for example, if you have, let's say, instead of a distributed generation, you have electric vehicles, and that might that will probably overload the transformer. Thermal loading does affect, and we can use inverse power law to determine the effect of thermal loading. But in this case, since we are only concerned with distributed generation in the form of solar PV, so the primary concern was to incorporate the information about mechanical stresses. But yes, the inverse power law can be expanded to include thermal stresses as well. Yes, so this survey results that came out of Australia 2 years ago, distribution transformers with OLTCs experience higher rates of failure after about 20 years of age. So previously it was thought that wear out usually begins to happen after 40 or 50 years of age, but this new data shows that it actually begins to occur far more earlier than thought.
That's with low penetration.
Yeah, that's with low penetration of solar PV. And as we have seen, the projections of solar PV here in Texas and around the world, if the chances of encountering these failures will keep on increasing. And given that we have thousands of these devices on our networks, it's possible that unless we take some steps, for example, we showed how solid state based devices can be used to reduce the stress on these devices, or in some cases, completely replace the devices. In that case, in the absence of that solutions, we'll encounter more and more failures, assuming that the DG penetration goes up in the future.
Read the question before you answer, because
so we have another question. All other things being equal, the variable parameter is the operation of tap changer contacts, which can lead to wear and tear, the flashover, and resultant failures within the transformer as a result of OLTC trying adjust as a result of variable voltage pattern from the DG. I'm not sure what the question is, but yes, since we have a highly variable voltage pattern, that pattern forces the regulator to operate much more frequently. As you've seen in those pictures, what happens to those tap changes, those tap operations, when you impose a very highly variable voltage on the OLTC, it forces it to regulate much more often than it normally would, and hence the reduction in its lifetime. So those are all the questions. If you still want to ask questions, you can unmute yourselves and ask them, or you can write them in the chat box if you want to.
maybe while we're waiting for the question, I could add a comment about thermal stress of the transformers. Akib mentioned the problems that may arise when, as we expect will happen soon, the load presented to distribution network by various electric vehicles locally charged will present totally different load on the transformers. That is a separate problem that needs to be added. In this presentation, we have tried to set a basic framework for approaching problems like this, where aging of the infrastructure and a gradual replacement and maintenance strategies can be of considerable importance. And pricing of the time lost due to prolonged outages or unexpected outages or outages of the critical loads, infrastructures that maintain communications, that maintain national security, cannot be allowed to experience such failure. So design of the system and the maintenance and scheduling of those events are accomplished in a way that secure certain level of reliability of operation and never get to the point of experiencing blackouts. However, we know from the experience that blackouts do occur, and not as frequently, the largest ones infrequently enough, but sufficiently closely spaced to remind us that no matter how much money and resources we put into designing systems that are resilient, they will still, in certain extraordinary cases, be exposed to widespread, large, and impactful blackouts, which is not the subject of this talk, but a reminder that that the entire realm that we are dealing with is a basically huge stochastic system that we can only address in a probabilistic fashion, and hope that the impactful unintended consequences are relatively infrequent. Any new questions?
So we have one that says, how did you select the viable parameters to fit your model?
In which part of the, I suppose it's in yours.
So in the second part, the viable parameters are actually estimated using the inference scheme that we showed and using the historical data that we have. So what we do is we incorporate the historical data to get the expected value of those parameters. We don't get the full posteriors of these parameters because there are no analytical solutions, no closed form solutions available. So we have to resort to the use of numerical integration. But we have also something that we haven't showed here that we are still working on is getting these full posteriors using computational algorithms such as Markov chain Monte Carlo methods, where we run a Markov chain to get the stationary distribution of that Markov chain. But in this case, what we did was we take the failure data that we have and use that data in our in the likelihood function that we saw in the slides, and get the expected value of those parameters and plug those parameters back into the failure model to make estimates about the remaining life of the transformers. Yes, many of the problems can be avoided when we have, if we consider smart inverters, but the DStatCom that we talked about has much superior performance than smart inverters, since smart inverters are limited in their capability of doing reactive power compensation, which is not, that limitation is not shared by the DStatCom device. It's true we can use smart inverters to do that, and which is why we have this a new category of solid state based devices that can be used, either a combination of DStatComs with smart inverters or smart inverters coordinating with each other to relieve the stress on these inverters. Yeah, and also as far as the DStatCom is concerned, this is a multifunctional device. So in addition to doing reactive power compensation, it can also do voltage control and also can do harmonic filtering, something which we can do with smart inverters. So we can perform all these multiple functions simultaneously while also at the same time making sure that we are relieving the stress on these regulators. Or if we have enough D-STAT-COMs, we can completely get rid of the mechanical regulators on our voltage feeders. But of course, that will involve a large initial investment, and that can be answered by doing a complete stochastic cost benefit. And it also depends on the utility, how much they are willing to invest on this device. So we have a question about, are there any standard rules for predictive maintenance in the industry?
There are many approaches, and utilities are very different from one another. But in general, what we can conclude if we analyze the experience and the approaches that utilities are doing to this, we see that the monitoring of the system condition of whatever infrastructure is being addressed typically does not include all of the factors. If I go back to the example of cables, several years ago, I participated in a very large-scale 5-year study of cable infrastructure. And cables have multiple mechanisms of aging that I've mentioned. The water trees that are penetrating into insulation may take years to provide failures, but may present themselves in the form of partial discharges in normal operation. And partial discharge can be detected by monitoring mechanisms and acted upon. However, when one looks at mechanisms that produce partial discharge, one can conclude after extensive collection of data that many partial discharges appear to be benign and do not produce imminent failures. So there are multiple classes of diagnostic tests that are being used to obtain an actionable information. That could be very low frequency over voltage tests, which tend to acceleratedly age cables in the form that would produce imminent failures to those that are very close to it, rather than waiting for it to happen at an inconvenient time. So designing appropriate diagnostic tests, performing sufficiently frequent but not too frequent maintenance produces probably the best economic effects. And this is an engineering problem. There is no perfect solution, because perfect solution requires infinite resources and infinitely closely spaced actions. We are trying, and we being all engineers working on problems similar to this one, trying to find a reasonably spaced monitoring events and diagnostic tests that would enable detection of the chunks of infrastructure that can be preemptively replaced to preclude large outages and prolonged lack of service to a variety of customers. And we are talking about regular customers. When we address issues of critical customers, of course, that's subject to completely different rules.
We have a question about, are the inference techniques used exact inference or any other approximate techniques explored? Since we add more variability affecting the failure rate, we may not always get exact inference. So the inference scheme that we have developed, we've tried to keep it very general so that it could be applied to other class of devices experiencing similar stresses. We're talking only about mechanical stresses and not the thermal or the electrical stresses. But one limitation is in the amount of data that we have, since the data on the failure of these transformers, particularly transformers that are equipped with low tap changers, that data is very scarce. And so the results of inference will be heavily affected by how much failure information you already have. As you've seen how the inference changes when you add more information. And it depends on what is your data set, how many devices you have. So you could have N devices, and N could be very large, but you could only know the failure times of a tiny percentage of them. In that case, your inference would not be exact. But as you keep, so it's an iterative process where you keep adding more failure information and you keep looking at the estimates, and at some point, the failure estimates would not necessarily change by much. So that's the point where you stop and we can say, in our case, for example, we had a data set of 40 transformers with low tap changers, and we knew the failure times of 20 of those transformers while 20 were still surviving. So the inference scheme works best when we have the failure information about 20 of those transformers. And if you keep adding more failure more failure times, then it doesn't necessarily change the failure estimates of the surviving group. Having data severely limits, if you don't have enough data, then you won't be in a position to do exact inference. I hope that answers the question. Another question about how much of transformer aging failure you're showing is related to regular overloading or the life prior to failure. I'm not sure what you're asking here, but the transformer, we ran you through a couple of results, a couple of surveys that were done on transformers distribution as well as transmission and transmission transformers. The results of those surveys show that for distribution transformers with voltage ratings of less than 66 kilovolts, aging failures usually dominate after about 20 years of age. Failures caused by overloading or failures caused by thermal stresses on windings or the failure of tank or dielectric, they are not as significant as failures related with OLTCs.
I think we're approaching now, actually, we're beyond the allotted time. So we should encourage people who have questions to send them via email, and we'll be happy. Sure.
Yes. And with that, thank you, Dr. Begovic and Akif, for this cutting-edge research presentation. Let me mention for the next webinar, it will be titled Electric Grid Operations Visual Storytelling, Past, Present, and Future, and it will be held by Dr. Thomas Obabi, professor at A&M at Electrical and Computer Engineering. It will be held on the 30th of March. So thank you for attending this webinar, and until we meet again, hope you stay safe. Thank you and goodbye.
Thank you all.
Goodbye.
Goodbye.